Okay, so now that we've looked at both delegates and return functions, it's time to look at using those for something more FMOD specific. We're going to start by learning about FMOD callbacks. However, I'm not going to be the one teaching you this lesson. A good friend of mine, Colin, is going to be the instructor for you, and he really knows his stuff, as you're about to see. He really understands these sort of back end and these deeper systems that FMOD uses for both callbacks and for programmer instruments, which is the topic of the lesson after this. I've just watched his lesson that he's created for callbacks. It's very impressive. The one thing I wanted to say is that I don't want you guys to worry too much about learning every single specific system, tool, and thing that Colin points out in this lesson. The main thing is we just want you to get confident with using these tools. So Colin's going to run you through them all and show you how you can create a really cool system where your game responds to your music, and we can change the color of our camera just by reading our FMOD event. So I'm going to leave you in the capable hands of Colin. As always, if you have any issues, our Discord is always available to you, or you can email me, of course, and I hope you enjoy.
Hi, I'm Colin Vandervort, also known as Colin v Audio, and I'll be helping Henry out for these next two lessons. If you're interested, I have a YouTube channel, Twitter, and Instagram page where I post about technical game audio implementation concepts and strategies. So in this lesson, we'll be unpacking FMOD event callbacks. I'll warn you ahead of time, the implementation for this topic gets pretty complicated and heady, but the example I'll be providing, as well as the one provided by the FMOD documentation, is pretty easy to copy-paste and get working at a basic level. I highly recommend doing the previous lessons before this one if you haven't, as we'll be building on a lot of previously covered material. So in most game design scenarios, audio is expected to respond or react to the events that are happening in the game. If you click a button, a UI sound is played. If a creature takes a step, a footstep sound is played. And if you enter combat in an action game, battle music generally starts playing. These are very common situations and are pretty easy implementation problems to reason about. However, sometimes we might want parts of our game to respond to something that's happening in our audio instead. It's the reverse of what we're used to. Examples of this can be found in pretty much any rhythm game where certain events are synchronized with the tempo or instrumentation in the music, but you'll also find cases such as in The Witcher 3, Blood and Wine, where enemy combat animations are being predictively assigned to line up with events in the music. There will be a link to a talk covering this particular example below the video. So event callbacks are the means FMOD uses to allow us to build these types of reactive systems. More specifically, event callbacks give us access to any tempo, bar, and beat information on our track in real time, as well as our current position along that track and any custom markers or time signature information that we have assigned to the track. Each time a change in any of these is detected, FMOD will call a function to send that new information to us in the game engine. We can then distribute this information to any systems that will be relying upon it. Today, I'll be walking through the method that's used in Unity for setting up callbacks on a music track, and then a common method for distributing that information to other systems. We'll be using one of these systems in our 3D adventure game to trigger some screen shake on the beat of our music in the final level 2 boss fight, and set up some post-processing color changes on the camera to match the current mood of our music. For reference, I'll be using FMOD version 2.01 and Unity version 2020.3. To start out, let's hop over into our FMOD project and create or select a music track. This will be easier to visualize if you're using a music track with a pronounced beat, and for that reason, I'll be using the battle music from the end of our second level in the 3D game kit. Make sure to add a timeline tab if you don't have one already, and place your music on it. Now right-click the Logic Tracks section in our timeline and add a tempo marker for each tempo or time signature in your track. In our case, this is 112 BPM at 4/4 time. We'll be using this tempo and time signature data to control our beat event callbacks and trigger our screen shake event. Additionally, make sure the track loops. From here, create a few destination markers and scatter them around your track. We won't be using these destination markers for any logical purpose within FMOD itself, but we will be using their string names to apply specific behaviors when they're reached. Place them in any section of your track where you'd like to highlight tonal shifts, and then give them a name. In my case, I'll be naming them directly after the post-processing colors I'll be applying to our camera when they're reached, but they can realistically be named anything. Chorus, verse, and bridge are some example names that could work. Intro, low intensity, and high intensity might also be good names. The only caveat is there cannot be two markers that share the same name back to back, or the second one won't be detected as a new marker by our system. Now, because I'll be mimicking the functionality that the Unity Battle Music already has, I'll be adding a global parameter entitled Music Section. This parameter will be used to fade our battle music in and out when we enter and exit our boss battle arena. The parameter will be continuous and mapped from 0 to 1. We'll assign our volume curve such that 0 is silent and 1 is full volume. If you already have general level music set up in your scene, you'll want to create the opposite automation curve on that music so that it fades out as the battle music fades in. In case you don't have this set up, I'll quickly walk through the creation of this event. Just like in our previous event, we'll import our music, name our event, and assign volume automation to the inverse of how it's assigned for our battle music. Additionally, I'll be applying AHDSR curves to both events to make sure they start and stop smoothly. Finally, we'll select our global parameter and set the seek speed to give us a gradual fade and simplify our implementation. Now, we'll assign our music events to their respective bank for level 2 and set up placement in our mixer. I'll just be assigning these to the master bank for now, but feel free to assign them to the respective banks if you have them set up. In my case, I'll also just be dropping the events into a music group and routing some of the music group signal to a reverb. Now let's build our banks and hop over to our level 2 scene in Unity. For our initial scene setup, let's make sure we have an FMOD Studio Listener component in our scene and an object to manage the loading of our FMOD banks. I'll be placing my listener on my primary camera and creating a standalone object for bank management. Additionally, I'll be muting the default implementation of our level music because I haven't disabled all of the stock audio in my scene. You can feel free to ignore this step if you have. Let's also make sure our banks are properly assigned in the FMOD Studio settings window, just in case. Now from here, we'll create a folder for our event callback scripts. We can name this folder anything that makes sense for the context of an organization of our project. I'll just be calling mine custom scripts for now. In this folder, I'll quickly create and add the music player script that you all put together in previous lessons. I'll now add an object into my scene, which I'll call gameplay music player. And I'll attach this script to it. If you don't already have your basic gameplay music player in your scene, follow along with this as well. And finally, I'll assign my basic gameplay music to this object. Now back to our scripts folder. Let's create a script and call it Music Manager. This script will handle our event callbacks functionality, as well as the music we'll be tying our callbacks to. In our case, this will be the battle music. Note that this could be combined with our music player script, but for the sake of clarity, we'll be splitting them up in this lesson. So now with our Music Manager script open, the very first thing we'll need to do is include a couple namespaces to use. We'll add the FMOD Unity namespace, as well as the namespace that's probably new to most of you, the system.runtime.interoperational services. The C# scripting language has us largely working within the confines of managed code. In other words, code that's sandboxed for us by a runtime framework, in this case the .NET framework. There are a lot of benefits to using managed code, including automatic garbage collection, which I'll talk about in a bit, but the main drawback is it prevents us from talking directly to the operating system and accessing low-level functionality, such as direct memory allocation. For our music manager, we need to be able to explicitly reserve a chunk of memory so that it won't be collected or moved by the garbage collector. This is needed because the FMOD event callbacks we're listening for exist outside of Unity's managed memory and are processed asynchronously from the rest of our game. Our only reliable access to them is through unmanaged code on our operating system. That all sounds pretty complex, I know, but to simplify it, we basically need to use some unmanaged memory to access data directly from the FMOD audio engine, and we need to tell the Unity automatic garbage collector to ignore that memory. But first, let's get our music set up. We will first need a variable in the editor for assigning our event to. Because I'm still using FMOD version 2.01, I'm using the event_ref tag here. If you're using FMOD 2.02 or later, this will have been replaced by an event_ref type, which will go in place of this string here. We'll also need a field for our global parameter. This looks similar to an event, but uses the param_ref type. And we'll also want to cache our parameter ID at some point because we'll be calling updates on our parameter frequently, so we'll need a variable for that as well. Apologies, let me zoom this all in. And finally, we'll need a variable to store the instance of our music in. This is the primary access point for most of what we will be doing. From here, we'll create a start function, and in the start function, we'll simply create an instance of our battle music and assign it to our instance variable. Additionally, we'll use the getParameterDescriptionByName function to capture our parameter description information from our music parameter event, and then we'll cache our music section parameter ID from the description into our respective parameter variable. Next, because we're assigning this instance manually, we'll also need to release it manually in order to avoid memory leaks. In this case, we can simply do this in an onDestroy function, which is called whenever the instance of this script is destroyed, or in other words, when an object in our scene containing this script is destroyed. In our case, this is at the end of our level. We'll also do a null check against our music event, not the instance, but the variable that's exposed in the inspector, to make sure that this is only ever run if something has been assigned as our music. This step is somewhat optional, but it's a nice safety check to prevent editor errors if your music hasn't been assigned yet. Now we can hook up our music in the editor. Jumping back over into our scene, let's create a new object for our music manager, as well as an object to act as a trigger zone for our battle music. We will place our battle music trigger at 103.23, 9.738.728, and 147.2741. And we'll give it a sphere collider with a radius of 27.04. If you're curious where I found these numbers, I'm copying them directly from the previous music trigger that was used with the stock Unity implementation. We'll also need to take our trigger object and set its layer to the environment layer and enable it as a trigger rather than a traditional collider. Both of those steps are super important for getting our logic to function properly. For more information on those, you can look into the Unity physics system. Now let's create our final script and call it Battle Music State Manager and attach this script to our trigger. We'll be using this script to trigger our shift between our game and our battle music when we enter and exit our trigger collider. All we need to add to this script are the stock onTriggerEnter and stock onTriggerExit functions, as well as a private layer mask variable that's visible in the editor. In both functions, we'll need to check to see if the layer mask contains anything at all, and also if there's any overlap between what is contained by the layer mask and our other layer. This formula looks a little strange, but essentially the value on the right-hand side of the equation will return as 0 only if there are no layer matches between our trigger collider and our layer mask. And if that's the case, we can ignore the collision from here. In the remaining cases, when the formula doesn't return 0, it means we've collided with a layer that is part of our layer mask, and we can execute the code within our if statement. If you want to know more about these sorts of logical comparisons, I suggest looking up C# logical operators and C# bitwise operators. It's also worth noting that in this operation, GameObject.layer, this right here, can be interpreted as an integer value by our compiler. If you want to see which integer value corresponds to a given layer, select any GameObject and open the layer dropdown. Their respective integer values are displayed next to the layer names. For example, our environment is on layer 16. For this next section, we will need access to our music manager from our Battle Music State Manager. Typically, you might create a field, a public or a serialized private field, and drag in the script component from our music manager, or do a get component call on start or awake. Instead, however, because we will also need access to a few specific functions in our music manager later on, and because we only ever want a single music manager in our scene, we're going to follow what is known as the singleton pattern for our music manager. In section 3 of the third module, we briefly covered singletons and statics. What we will be doing here is saving a static instance of our music manager class into our scene. All we need to do for this is create a public static variable with the type of our script's class. We'll name this variable instance. And now on awake in our script, we'll set our instance equal to the keyword this. The this keyword is a reference to this specific instance of our class. But because the singleton pattern starts to break if we ever have more than one copy of a static instance in our scene, we must first check to make sure that our instance variable hasn't yet been assigned. If it has been assigned, that means we're attempting to overwrite an existing static instance. So instead, we'll destroy this current instance, which is the newer one. Otherwise, we'll assign this instance as our static instance. In short, this guarantees that we'll always only have one instance of this class in our scene, and it will always be the oldest copy of that instance possible. Newer copies will always be destroyed on awake. What we can do now is access public fields and functions from our music manager from anywhere in our scene, even if those fields and functions aren't static themselves. Let's start by creating a public function in our music manager that will react to our trigger volume and set our music selection parameter based on whether we're entering or leaving our volume. We'll name this function setGlobalMusicParameter, and we'll give it an input type of a float called value. Now, moving back into our Battle Music State Manager, all we have to do to transition our music between gameplay and battle music when we enter or leave this trigger volume is pass our parameter setting function a 0 or a 1. The seek speed on the parameter that we have set up in FMOD will handle the gradual fades for this transition. To access this function, we simply query the music manager type, and from there we can directly access any statics it holds. This means we can directly access whichever static instance of this class currently exists in the scene. Now through that instance, we can call our setGlobalMusicParameter function and pass it a 1 for entering the trigger and a 0 for leaving it. In case an instance hasn't been assigned yet, we also may wish to do a quick null check as well. Finally, moving back to Music Manager, let's fill in our setGlobalMusicParameter function. All we need to do here, in order to set the parameter, is call setParameterById through Studio System in the Runtime Manager namespace, and pass in our parameter ID, which we cached earlier, and the value we've received from our trigger functions. You may notice, however, that we're still not starting the battle music anywhere. We'd like to start our battle music only on the first entry of our trigger collider. To set this up, we can create a simple private function called start battle music. Do a quick null check against our battle music event reference, and then check the state of our music instance using get playback state. Get playback state uses the out prefix, which indicates that it's returning a value rather than requesting one. You'll see this used frequently when the actual return type of a function is being reserved for something else, such as, in this case, a function execution result, or sometimes a Boolean true or false. This is common in functions that contain expensive calculations, but also have failure conditions, or cases where the calculations can be skipped, and notifications that the function has skipped a calculation matter to our end result. We can inline a variable declaration here, meaning the value of our output variable is being immediately assigned as a new variable within the current scope. And to do that, we simply place the type in front of the variable. The output type is a custom FMOD type, playback state. This is simply an enum that tells us what state the music is currently in. In our case, we want to see if the music is either stopped or stopping. If so, we haven't yet started the music, so we should do so. Now, all we need to do is confirm that our parameter value was a 1, or in other words, that we're entering our music trigger, and if so, we call this new private function to start our music. Hopping back over into the editor, let's double check that our battle music event and our global parameters are properly assigned on our music manager object. And with that, our music should be hooked up and working. To test, I'm going to go ahead and move Ellen into the hallway right before the final battle encounter. One final thing to check is the layers field on our battle music state manager. Make sure this is assigned to the player layer. Now let's test the game. If everything is working properly, the music should start as we enter the final room, fade out if we leave, and fade back in if we enter again. Perfect. Everything seems to be working. We can now move on to the complicated part of this lesson, building a system for receiving event callbacks from our music event. The way the system will function is every time a new beat event or FMOD marker is detected on our event instance timeline, the system will call a delegate function, which our script will be tied to, and will pass us whatever available data it has with respect to markers or our timeline. In other words, we're simply setting up a system that listens to changes on our timeline. Now, the first thing we'll need for this system is somewhere to store our data. We'll start by creating a class within our music manager script, which we'll call timeline info. To start, we'll add a public integer for our current beat and a public FMOD string wrapper, a custom FMOD string type for our last marker reached. Next, we'll create a variable for the instance of this timeline info, as well as a variable from our interoperational services namespace, a GC handle, short for garbage collector handle. We'll name this GC handle timeline handle. GC handles are entry points into specific chunks of unmanaged memory. Normally, memory is accessed directly or through pointers. GC handles are kind of like pointers, but they add restrictions that enable them to bridge managed and unmanaged memory spaces. In other words, bridge our code here with FMOD's internal systems. In our case, we'll be using our GC handle to allocate space for our timeline info and pin it in memory, allowing us to easily write to it from our operating system level systems without needing to worry about garbage collection, cleaning up, or moving the memory associated with our timeline info. Now, garbage collection is the process of scanning through memory and finding all of the chunks of memory that are no longer needed or assigned to any value that's in use, and marking those chunks of memory as memory that's free to be used again. Unity uses an automatic garbage collection system by default that will also periodically reorganize chunks of memory to create larger consecutive chunks of free memory for use. If the memory we were trying to write to for our timeline info was to move due to this process, it's very likely we would miss out on some callback information or run into strange and unexplainable behaviors, as the data our timeline info is receiving writes from is our streamed audio, which runs independently from our game's runtime and thus our garbage collector. In other words, we could run into problems if FMOD tried to write to our timeline info, as the automatic garbage collector was attempting to reorganize where that timeline info is being stored in memory. Because we will be pinning our timeline info to memory, we also need to specify how timeline info will be organized in memory. In our case, we can simply accomplish this by adding the struct layoutKind.sequential tag to our timeline info, indicating that it will have a predictable, unchanging sequence in memory. We also need to make sure that each data type in our class in memory is blittable. A blittable type is simply a type that is known by both the system and the application. In our case, by both our operating system and by Unity. Fortunately, all the types we'll be using are blittable, so this won't be relevant to know in depth for this lesson, and probably for future applications of this system, but it's worth knowing if you'd like to dig deeper into how these types of interoperational systems work. Finally, we'll also need a variable for our event callbacks. This is where we'll store our delegate object, ensuring it isn't caught up in garbage collection. Now that we have all of our event callback system variables prepared, we can move on to setting up the initialization for our event callback system itself. First, we'll simply instantiate a new default timeline info class and save it into our timeline info private variable. We will also do the same thing for our beat callback variable, but this is where things start to get pretty interesting. The type we save into beat callback is an event callback. Event callbacks are delegates. This means that the field we need to pass into our new event callback is a function itself, specifically the function that will be receiving and processing our raw callback data. This function doesn't exist within the FMOD API, so we'll need to create it ourselves. If you ever need a quick reference of this function, it can be found in the FMOD Unity integration scripting examples under timeline callbacks. We'll be naming this function beatEventCallback. To start, we'll make our function private, static, because we'll only ever need this function in this script, and we'll only ever want one instance of it to exist. And the return type of this function is an FMOD result, which is simply a custom FMOD enum that returns specific values depending on the result of the execution. For example, if the function succeeds in executing as expected, it will generally return a result.ok. We'll name our function. In this case, it'll be named beatEventCallback. It will require 3 inputs: an event callback type, a pointer to our music event instance, and a pointer to our music event parameters, which hold the event data of our event instance. This can be a little confusing because these parameters are not the same as the parameters we usually talk about within FMOD. As you can see, we're getting an error on int pointer, and that's because we have not yet included the proper namespace. In other words, we're not using system. Now, the first thing we'll need to do in this function is we'll need to copy in a new event instance from our instance pointer. Next, we'll capture the pointer to the place in memory where our current event instance data is being held with the getUserData method. We'll also store our result here. We will do a safety check to see if anything went wrong so far, and log an error if so. If not, we'll continue. And assuming our pointer is looking at anything relevant, intPointer.0 is effectively a pointer-specific null check. We'll save a new GC handle to access our event data through. Using this GC handle, we'll then finally directly grab the timeline info using the .target property. This simply grabs the object our GC handle is connected to. Next, we'll create a switch statement to check the type of event callback we've received. We'll create two separate cases, one if our type is a beat event, and one if it registers a marker. Inside both of these cases, we'll create a parameter variable, which will hold our beat properties and marker properties respectively. Again, this type of parameter we're talking about is a programmatic parameter. It's just a stream of data. The properties data types generally encompass all of the different types of data that can be returned with their respective type of callback. Now, the data we care about is currently located in our parameter pointer. The final functional input that I mentioned held our event instance data. Because this data is still in unmanaged memory, and we're now working in the land of managed memory, we'll need to use the Marshal class from the Interoperational Services namespace to copy over that data. We use the Marshal.pointerToStructure, which takes an input of our pointer into memory, our parameter pointer, as well as the type of output we are looking for. Now, because pointer-to-structure returns a generic object, even if we specify a type to return, we need to also cast this object as the respective type we were searching for. And with that, we finally have access to our event callback data in managed memory. From here, we can simply save values from parameter, our data, straight into our local timeline info variable. In the beat section, we'll be saving parameter.beat into timelineInfo.currentBeat. And in the marker section, we'll save parameter.name, the name of the most recent marker, into our timelineInfo.lastMarker. Now you may have noticed there are a few other types of data we have access to on beat and on marker event. I'm going to go ahead and fill in the rest of these just so you're able to see them. I'll also add them to my timeline info as well. Feel free to follow along, but know that none of these additional values are required for what we'll be doing today. Finally, assuming all of our code in our beat event callback function has been executed properly till this point, we can safely return an FMOD.result of OK at the end of the function. And with that, the difficult and hyper-confusing part of this is over. It's okay if you don't completely understand everything that's happening here. Most likely, you'll never need to in order to be able to use this system, but if you're curious, there will be a number of links below that you can dig into that might help you develop a deeper understanding of what's happening here, should you need to extend this system or modify it in the future. Now to wrap this system up, let's move back to our start function. You may recall that I mentioned before that we need to pin our timeline handle into unmanaged memory, but we still haven't done that. Let's go ahead and do that now using the gchandle.allocate method. Additionally, we also need to tell our music event instance where this timeline handle is in unmanaged memory. And finally, we'll set our beat callback variable as the callback variable our event instance should pay attention to, and specify that it should send callbacks on both beat and marker events. I'll also quickly grab and store our track length from our event description on start, though we won't be using this directly today. And I'll store it in another private variable. Now, before we forget, let's also make sure we zero out the rest of our manually assigned memory values on destroy. First, let's set the pointer for our user data to intPointer.0. Also, if we're not already, it might be good to make sure our music instance stops playing here. You can give it an immediate fade or allow a custom fade depending on what's needed. finally, we need to free our timeline handle memory allocation. We can simply use the free function here. And with that, our beat and marker detection event callback system is fully set up and ready to test. Now we could test this using debug statements on update, but that's kind of flimsy and can be difficult to look at when monitoring multiple types of information. So instead, let's create an onGUI function. OnGUI is a function that's great for quickly rendering UI information in Unity. It's great for testing and prototyping specific types of features very quickly. In this case, we'll simply create a GUI layout box that will by default display in the upper left-hand corner of the screen during runtime. Inside this box, we'll write our debug info as a string, but to make this a little easier to work with, we'll use the C# systems namespace's custom string.format function. This function allows us to specify object values to print directly as strings in a field. We'll start by typing in quotes current beat equals curly brackets, a 0 for our first field, our first object field, and then last marker equals some more curly braces and a 1 representing our second object field. We'll then end our quotations, add a comma, and then our first object, timelineinfo.currentBeat, another comma, and our second object, timelineinfo.lastMarker. And for last marker, we need to specify explicitly that this is a string. Now, these are the only chunks of data that we're going to be using for our current system. I'm going to go ahead and reorganize this for all the additional optional fields that I added earlier as well. Again, feel free to do the same. Either way, we basically have a functional onGUI display now. One final thing we can add is a surrounding Unity editor if statement, denoting that this code will only run if we're in the editor itself. The syntax for this is a little different, but what this means is this code will only run if we're in the editor. It will not run if we're in an actual build of the game. Now let's jump back into Unity and quickly open up our FMOD settings panel. Under Play in Editor settings, make sure you disable your debug overlay as it overlaps with our onGUI display. Now we can test our game. Once we run into an area where our music is triggered, you should now see the beats and markers being updated in the upper left corner of your game. Great! Now we have working beat and marker detection based on event callbacks. Now, how do we use these? We've talked about delegates a few times, including in previous lessons. However, we may not have touched on event delegates specifically. Events are essentially a special type of delegate that allow for safe external subscription to a behavior. In other words, we can create our own event callback by creating an event delegate that fires in our music manager each time a marker or beat change is found, and then subscribe external functions to this event in order to trigger them reactively. In our case, we'll build 2 functions to trigger screen shake on our beat events and color changes to our camera overlay on custom marker detection. Back in our music manager script, let's create 2 public delegates with void return types. Have one define a beat event delegate type and have this require that an integer beat value be passed through it. And let's do the same for our marker event delegate and require a string for the marker name to be passed through it. Let's create a public static event of type beat event delegate and one of type marker event delegate. We'll name these beat updated and marker updated respectively. Finally, because we only want these to fire off calls when a beat or a marker changes, let's add a private variable to store the last beat and the previous marker detected. Set these to 0 and an empty string respectively. Now let's create an update function to check for these changes. Let's create 2 if checks comparing our last beat and last marker to see if they are different from what's currently registered in our timeline info. If these pass, we'll update our last beat and last marker with the new values we just found. And if our beat updated and marker updated events are not null, we can call both of those and pass in the respective beat and marker data values from our timeline info class. With that, we should have universal access across our entire project to events that fire every time a change in a beat or a marker is detected. Now let's go about scheduling these events in order to test their functionality. So let's create one more new script, and we'll call this script Music Event Listener. In order to test our events, we only really need 4 functions. We'll add a start and onDestroy function, and we'll create 2 custom private functions called onBeat and onMarker that take an integer and a string value respectively and return void. In order to subscribe a function to an event, you simply add it to the event. To unsubscribe, you subtract it. Because our events are static, we can do this directly. In Start, through our Music Manager class, grab our beat and marker updated events and subscribe our onBeat and onMarker functions to them. OnDestroy will do the same thing, but this time we will unsubscribe. Now, onBeat will create a debug statement and we'll simply tell it to print our integer value for our beat. Let's do the same thing for our onMarker, but this time with our marker string name. Now we're ready to test. Simply add this new Music Event Listener script to any object in your scene, press play, and it should work. I'll be adding mine to my camera brain under my camera rig, as I'll show off an applied example there in a minute. Now, press play and navigate to your music trigger, and you should start to see a printout of the beat and marker values that match those from your onGUI display. Congratulations! You now have a working beat and marker detection system. You're most of the way to having the foundations of most rhythm games set up. To highlight this, I'm going to quickly extend the script we made to push color changes to our post-processing layer, as well as add a bit of screen shake on the beat of our music. Feel free to follow along, though I won't necessarily be explaining all the details of the subsystems we'll be using here. So first, I'll be adding the unityengine.rendering.postprocessing namespace to this script to give myself access to our color filter. Next, I'll create a field to add the camera post-processing volume to. Additionally, I'll add a float for an internal timer I'll be using for interpolation. I'll cache a record of our default color value, as well as a custom orange value, because Unity doesn't store one by default, and I would like to use orange here. I'll create a field to store a color grading variable into, which we'll use to set our color filter value through. And finally, I'll create a variable for our target color and our old color, which we'll be using for color interpolation. I'll also be assigning our default color as their default values. Now on start, I'll pull our color grading from our post-processing volume, assuming it's not equal to null. And on update, I'll set the value of our color filter to the current interpolated value between our old color and our new color with respect to our timer t divided by 1.867. 1.867 is a rough subdivision of the battle music BPM that I'm using. And after this, I'll increment our time variable t by time.deltaTime, the duration of one frame update. This simply makes our interpolation frame rate independent. Now, whenever a marker is called, I'll set our old color equal to our target color and reset our timer t to 0. From here, I'll create a switch statement and pass in our marker name. If you recall from the start of the lesson, I set up my markers as color values. Depending on which color we read in, I'll set our target color to a cached color value to represent that color. Just in case, I'll also set a default for our switch to return the default color. And finally, on beat, I'll simply use a built-in 3D GameKit function under the camera shake namespace called shake and pass it a small impulse and a small duration. And that's all we really need. Hopping back into the editor, let's make sure our post-processing volume is assigned, and then we'll test. I'll drag my camera into the volume field. And as you can see, we now have a small camera shake on beat, and each time the music reaches a new marker, we're shifting the post-process color filter to a new color. As I've mentioned a few times now, this is a lot of material, and likely a lot of new material as well. A lot of what we covered requires a pretty deep understanding of operating system level code, compilers, audio engines, and computer hardware to fully understand. That said, with what we've covered in this lesson, you should be able to at least have a general idea of what's happening with this system, and though it may take a bit to settle in, I hope you feel comfortable using event callbacks when you need them. To summarize, event callbacks are an incredibly powerful way to build unique experiences and create gameplay that reacts to audio, rather than just having audio react to gameplay. The next lesson will build on much of the material we covered here, and I promise it'll be at least the slightest bit less complicated. If you do have any concerns or questions about the material we've covered here, please feel free to ask about them in the Discord.